Matter's state is dictated by intermolecular forces and thermal energy. Understanding these interactions helps us comprehend the behaviors of liquids and gases, crucial in scientific studies. Intermolecular forces, excluding covalent bonds and ionic attractions, govern molecular interactions. Van der Waals forces, encompassing London forces and dipole interactions, play a pivotal role in anionic attraction. Hydrogen bonding, a distinct dipole-dipole interaction, involves specific elements. Ion dipole forces, separate from van der Waals forces, demonstrate unique interactions between ions and polar molecules. London forces, arising from momentary dipoles in nonpolar atoms, illustrate how temporary asymmetrical charge distributions induce polarity in neighboring atoms, leading to transient attractions. Fritz London identified temporary dipole attractions, known as London forces. These short-range forces depend on particle polarizability, significantly influencing molecular interactions at close distances. Dipole-dipole forces occur between molecules with permanent dipoles. These forces, involving partial charges, are weaker than ionic interactions but stronger than London forces, influencing molecular arrangements. Dipole-dipole forces are stronger than London forces but weaker than ionic interactions. Their energy decreases with distance, yet cumulative effects can enhance intermolecular forces in polar molecules. Dipole-induced dipole forces arise when polar molecules induce dipoles in nonpolar molecules. Interaction energy follows an inverse relationship with distance, emphasizing proximity's role in these attractions. Dipole-induced dipole strength depends on polar molecule dipole moment and neutral molecule polarizability. Larger molecules exhibit higher polarizability, enhancing these attractive intermolecular forces. Hydrogen bonds, strong dipole-dipole interactions, form in molecules with NH, OH, or HF bonds. These significant forces affect compound structures, notably in proteins and nucleic acids. Hydrogen bond strength relies on the Coulombic interactions between lone pair electrons and hydrogen atoms, significantly impacting molecular structures and properties, as seen in the HF hydrogen bond example. Repulsive forces counteract attractive interactions at close molecular proximities. Rising rapidly with proximity, these forces explain liquids and solids' resistance to compression, maintaining structural integrity. Thermal energy, proportional to temperature, arises from particle motion. It measures average kinetic energy, driving particle movement and influencing matter's state and intermolecular interactions. Intermolecular forces oppose thermal energy, determining matter's state. Weak interactions prevent liquid or solid formation unless temperature lowers, emphasizing the balance between these opposing forces. Gases don't liquefy under compression alone. Lowering temperature reduces thermal energy, facilitating liquefaction, highlighting the energy balance in different states of matter. Gases, the simplest state of matter, envelop us in the troposphere. This vital atmospheric layer, held by gravity, contains essential gases like oxygen and nitrogen for life. Only 11 elements exist as gases under normal conditions. Understanding their behavior under specific temperature and pressure conditions is crucial for studying gaseous states. Gases, with high compressibility and low density, expand to fill containers. Their molecules diffuse easily, mixing with other gases, demonstrating their distinct physical properties. Gas laws describe relationships between pressure, volume, and temperature. Boyle's, Charles, and Avogadro's laws provide foundational insights into gas behavior under varying conditions. The ideal gas equation assumes no molecular volume or forces, predicting gas behavior. However, real gases deviate, especially under high pressure or low temperature, limiting its accuracy. Real gases deviate from ideal behavior due to molecular size and intermolecular forces. The van der Waals equation accounts for these factors, providing a more accurate description. Kinetic molecular theory explains gas behavior, constant motion, elastic collisions, negligible forces, and temperature proportional kinetic energy. This theory underpins our understanding of gases. Liquids are intermediate between gases and solids, with molecules closely packed but freely moving. Their fluidity and incompressibility make them unique among states of matter. Liquids exhibit surface tension, viscosity, and vapor pressure. These properties arise from intermolecular forces influencing liquid behavior and applications in various scientific fields. Evaporation transforms liquids into vapor below boiling points, while condensation reverses this process. In closed systems, they achieve dynamic equilibrium, maintaining liquid-vapor balance. Boiling and freezing points depend on atmospheric pressure. Changes in pressure alter these points, influencing phase transitions and providing insights into matter's thermal behavior. In liquids, van der Waals forces, hydrogen bonding, and ionic interactions govern molecular cohesion. These forces determine liquid properties and behavior in various environments. Liquid crystals, with properties of both liquids and solids, come in nematic, smectic, and cholesteric types. Their unique characteristics find applications in displays and sensors. Phase transitions, like melting, vaporization, sublimation, and deposition, illustrate state changes. Understanding these processes is vital for manipulating matter in scientific and industrial applications. States of matter result from intermolecular forces and thermal energy balance. Temperature and pressure changes drive transitions, crucial for scientific and technological advancements.